Hello everyone. In this video, we will discuss waveform symmetries, odd, even, and half wave. We also talk about summation notation, definition of Fourier series, its constant, Fourier coefficients, and the effect of symmetries on Fourier series of certain waveforms. Let's start with odd functions. Odd function represented by a graph which is symmetric about the origin. If I have a function fx and I evaluate f at the value of negative x, then if negative f of negative x equal to fx for any value of x, then that function is an odd function. One obvious odd function is the sine function y equal to sine x. So let's examine this graph that I have on this figure. So I will draw one cycle of sine. So let's reconnect this. Okay, from pi to negative pi. So right here is negative pi, right here is pi. I have one cycle of this sine function. So what I will do is I will draw a line through the origin to show you that it actually is the odd function in this case. Okay, so I start from here. I will draw a line through its origin. Okay, just so that you see that it's symmetric through the origin. So let's use some number to prove that I have fx is equal to negative f of negative x. So what I will do is I will pick the value 0.5 pi. So right here, I pick these values. Okay. So I will let x equal to 0.5 pi. Okay. Then what I have for sine of 0.5 pi will be equal to 1. So which is this values right here. Okay. So right here I will have 0.5 pi, and here I have 1. So sine of that is equal to 1. Then what I will do is I will evaluate sine of negative 0.5 pi. Okay, so now let x equal to negative 0.5 pi. What do I get? So we go on the graph. I project it to here. This point I should write it as negative 0.5 pi and negative 1. So in this case, I should have negative 1. And what I will do with this equations here is, okay, so this equation right here, I will divide it by negative 1. So I will write sine of negative 0.5 pi divided by minus 1 equal to minus 1 divided by minus 1. Therefore, what I see is I should have negative sine of negative 0.5 pi equal to 1. Then I would like you to compare this equation with this equation. Because I have both sides equal to 1, so I can let them equal to each other. Okay, so therefore I have sine of 0.5 pi. So let's put this in a bracket. Will be equal to negative sine of negative 0.5 pi. So I have proven according to the definition. The definition said that given the function fx, in this case is sine of x, if I take the negative values of x, which is negative 0.5, I evaluate that is equal to negative f of x, then I have proven that this is an odd function. So in this case, sine is an odd function. Alright, So let's move on to the even function. So for the even function, the definition said that the graph is symmetric about the y-axis. So this is quite obvious for us to recognize. Alright, so I'm going to highlight this portion of the graph y equal to cos x. And I would like you to note that this part right here is the exact equal to the other part. So they are exactly equal to each other through the y-axis. Okay, so let's prove that. Let's prove that because the definition for this would say fx equal to f of negative x. So I will pick certain value of x again, and I will evaluate this function y equal to cos of x. Okay, so I will pick the value of negative 0.25. So I will pick these values right here. I project it up here. I should have it equal to 0.707. So negative of 0.25 pi will give me 0.707 for the y. So cos of 0.25 pi will give me 0.707. So in a way that I would like to mention to everyone that this is root 2 divided by 2. Okay, and then what I do next is I will take cos of negative 0.25 pi to see if it's still equal to 0.707. Okay, so what I do is I take this 0.5, I project it up here. So then you see this is the exact same. So I also have the value of 0.707. So this is 0.25 pi. Okay, so in this case, what I have is taking the positive 0.25 pi, I have 0.707. Take the negative 0.25 pi, I also end up with 0.707. So it is the same. Okay, so in that sense, I conclude that so the function fx is equal to f of negative x. Right? So this is an even function. So in a way, sine is an odd function and cos is an even function. So if a function does not satisfy the two above conditions, then we can say that the function is neither even nor odd. All right? But we are not going to deal with that situation in this class. So the next one I would like to mention to everyone is the halfway symmetry. Okay, so halfway symmetry said that the negative half cycle has the same shape as the positive half cycle. So the formulas for that would be like this. Okay, and remind to everyone that sine graph is halfway symmetry and it is odd. The sine graph is halfway symmetry and it is odd. The cosine graph is also halfway symmetry and it is even. So let's prove that the positive half is equal to the negative half. So now you see this one is a sine graph, right? So this one is a sine graph. Okay, so let's check if the negative half is equal to the positive half. So I divide this negative part in half. Okay, so right here. And I divide this positive part in half as well. And now you see that they are actually equal to each other. So this is defined as halfway symmetry. Sine graph is halfway symmetry and it's odd. Okay, now cosine. Let's take a look at the negative half of cosine and compare with the positive half of cosine. So I will pick this part. This one is a negative half of cosine, because this part is in fact on the negative part of x. So that is the values here. So, and then I pick the positive part of cosine. So they are equal to each other. So this one is a cosine graph. Okay, and it's actually even. So they both have halfway symmetry, and one is odd and one is even. So we keep that in mind, okay, because they fit into the definition of the negative half cycle had the same shape as the positive half cycle. All right, so keep all of that terminology in our minds. All right, okay. So in the note here, I would like to write that halfway symmetry, so the negative half cycle is the same as positive half cycle. Okay. All right. So let's move on to our summation notation. Working with summation notation is just something new, and it's just a shortcut representing that you have to add something together. That's why it's called summation. Okay, so if I have this notation right here, it's called the summation. Then I would like to add a few terms together. Given n equal to 1 to 4, so that means you should have 4 terms in this case, okay? So you will find when n equal to 1, n equal to 2, n equal to 3, and n equal to 4. So in this case, what you do is you will write the expansion of this sum. So when n equal to 1, I should have 1 over 1 plus 1. And then when n equal to 2, I should have 2 over 2 plus 1. When n equal to 3, I should have 3 over 3 plus 1. And when n equal to 4, I should have 4 over 4 plus 1. All right? Okay. So let's keep this in mind. So, and I have to expand and simplify if possible. So I have to simplify that. So I should have a half plus 2 over 3 plus 3 over 4 plus 4 over 5. So in this case, I should have the common denominator of 60, and I should have it as 60, 30 plus 40 plus 45 plus 48. The final answer should be 163 over 60. Okay, so the summations, again, just to remind everyone, the summation is the abbreviation, and it's telling you how many terms that you have to expand. So here is the number n, tell you from 1 to 4. N is an integer, keep that in mind. Okay, so that means you should have 4 terms. And since given n here as your in the formula, and the formula, all you have to substitute the value for n and expand them into 4 terms and calculate the result. Okay, so let's start with the next summation. So now in this summation, what I have is n is an integer, so n will be 1, n will be 2, will be 3, will be 4, and will be 5. Okay, so all you do is just expand this with 5 terms. So take a look at this n that's given to me. So the first n will be n equal to 1. So I would write 1 pi times over period. Okay, I add that with 2 times pi times time over the period t. And I will add that with 3 times pi times t divided by period t. And I will have 4 pi t over period plus 5 pi t over period of t. So adding them up, I have the same denominators of period t. So I should have 1 pi t plus 2 pi t plus 3 pi t plus 4 pi t plus 5 pi t. So then I should have it equal to 15 pi t over period, or I can pull the constant to the front. I can write this as the answer as well. Okay, so we will see all of this again in our Fourier series lesson. So it's a good idea that to go over the summation notation. All right, so this is one of the summation which is very important. Okay, so in this case what I have is summation from n equal to 1 to 3 of an cosine of 2 pi n times t divided by period t. So you see that you will have 3 terms in this case, because you will have n equal to 1, n equal to 2, and n equal to 3. Don't forget n is an integer. And then where you find the n, you substitute in the n for the value for that. Okay, so when n equal to 1, I have that. When n equal to 2, I have this term. When n equal to 3, I have this term. And my next line here is that I take 1 times 2, I got 2. I take 2 times 2, I got 4. I got 3 times 2, I got 6. Okay, so part of that is we simplify our expression. We will see all of this notation again in our Fourier series lessons. Alright, so let's move on and talk about Fourier series. Yeah, you can see this right away in the definition of Fourier series. Okay, so definition of Fourier series, what I have in this case is I am having fx equal to a naught divided by 2 plus the summation of n to infinity of an times cos of nx plus bn times sine of nx. Okay, so in this case what you have is you have an a naught, okay, you have an an, you have a bn. These are the important factors of Fourier series. I would say a naught is the constant term. Okay, so this one is the constant term. Okay, constant term because it's just by itself. It does not attach itself to any function. Like in this case, you see an attached to cos of nx and bn attached to sine of nx. So an becomes the coefficient and bn becomes the coefficient. So this is called the Fourier coefficients. Okay, Fourier coefficient, because they are coefficient of certain function, and if you add those functions, it will end up to be a Fourier series. Okay, why is it a series? Because you have so many terms. So in this case, you see I represent this as a summation. That means I will let n equal to 1. See here, n equal to 1. You have cos of 1x. If n equal to 2, you have cos of 2x. If n equal to 3, you have cos of 3x, and so on. And then I have b1 times sine of 1x. I have b2 times sine of 2x, b3 sine of 3x, and so on. Alright? Okay. So this is the expansion of Fourier series. So this is the expansion. Abbreviation for that, you would write it in the summation notation. Okay, so depends on how many terms that I ask you to write for this Fourier series. It will be defined for you by n equal to 1 to certain number instead of the infinities. Alright, okay. So now talk about an and bn. So if we talk about an and bn, there are formulas to calculate AN, to calculate BN, and formula to calculate A0. Okay, so this one is A0. So to calculate A0 of a function fx, I would write 1 over pi multiplied by integral from negative pi to pi, given negative pi to pi are 1 full period, and this function is repeating itself after 1 full period. So I will take the integral of this function fx in terms of x, evaluate from the negative pi to pi. So don't forget, this is definite integral that we are talking about. Okay, to calculate an, what I need to do is, again, I have to have 1 over pi multiplied by the integral, calculate from negative pi to pi, of a function fx. In this case, because I'm calculating an, I must multiply that with cosine of nx as the argument, and you know that dx always attached with the integral sign to tell you that you have to integrate in terms of x. To calculate bn, okay, calculate bn, which is the Fourier coefficient. So to calculate bn, what you do is you multiply the integral with 1 over pi again, evaluate from negative pi to pi of a function fx. This time you multiply by sine of n of x as the argument, evaluate as a function of x. That's why you put dx. Okay, so let's go over the terminology again. A0 is called the constant term. A1 times cos of 1, or B1 times sine of x, cos of 1x, sine of 1x, then this is called the fundamentals. So each of this term right here has its own unique name. Okay, so you see the coefficient start with the 2, and the B2, this is called the second harmonics. Each of this term is called the harmonics. So the 3 and the 3, B3 and sine of 3x is called the third harmonic. The A4 cos of 4x, B4 cos of 4x, this one is called the fourth harmonics. And if it's a 5, it's called the fifth harmonics, and so on. So it's just a terminology that we have to remember. Alright, okay. So what we have here is, again, A0 is a constant term. The very first term in the Fourier series, if you have A1 and B1, it's called the fundamental. As soon as you have like A2, B2, A3, B3, then you start counting them each term as the second, the third, or the fourth harmonics. Okay, there's some very important term that I would like everyone to remember. Waveform is odd symmetry. Okay, if you found the waveform is odd, in this case, it should be a. So let's go back to review. Okay, so in here, what we have is sine is odd, right? And cosine is an even. Sine is an odd function. Cosine is an even function. So if the waveform is an odd, then you only have the sine term. So it's easy to remember, right? So if a function or a waveform has an odd symmetry, then it's only have the sine term. The Fourier series will not have any constant and no cosine term. If the waveform has an even symmetry, then you only have the cosine, because cos is even, and no sine term in this case, and in some cases you may have the constant term. If the waveform is halfway, okay, it has a halfway symmetry, then you only have the odd harmonics and no even harmonics. So what does that mean? Odd harmonics, that means you either have A3, B3, A5, B5, but you will not have like A2, B2, A4, B4. So again, just a reminder to everyone, okay, sine is odd, okay, and cosine is even, okay. And that helps us to remember that if a waveform has an odd symmetry, then we only have sine term for Fourier series. If a waveform is even, then we only have cosine term for its Fourier series. Okay, all of these will be clarified in the next lesson that we are doing. Alright, okay. So if the waveform is half-wave symmetry, then we only have odd harmonics. Okay, odd harmonics is when you are having A3 times cos of 3x or B3 times sine of 3x, or you could have A5 times cos of 5x, B5 times sine of 5x. Alright, so Fourier series consists of this series right here. Okay, and depends on the symmetry of your waveform, you can eliminate some of this term. Alright, thank you.